Hello, everybody. Everyone sleep well, well rested, well fed, lots of pork products. All right. Because there's a bit of a mix here, I'm just going to ask for like a raise of hands. How many people are familiar with the concept of a tuple space? Okay. How many people were familiar with the concept of a tuple space before they heard of our chain? Okay, only a handful. And how many people are familiar with the Special K project? Okay, so we can explain some of these things. All right, so the basic idea of a tuple space dates back to the 80s. There was a guy named Bruce Galertner who wrote a programming language called Linda, and he came up with this associated memory paradigm where he was basically pushing keys and values, like a key value store, into a sort of distributed repository, and that this was a way for many computers or many machines to communicate in network using this tuple space. And the idea like took off a bit. There was like Greg likes to talk about how there was a cottage industry of tuple space implementations in the 90s. I sort of think of it as in the sort of somewhat in the same sphere as the sort of utopian days of Smalltalk and Prolog and Lisp machines and things like that. But the idea hasn't really had so much traction in recent years. So then Greg in the mid-2000s was working on an embedding of some of the same ideas that you find in Rolang in Scala as like essentially an embedded domain-specific language in Scala. And that's what Special K is, but Special K is also can be kind of seen as kind of a tuple space. And so in a tuple space, you would have this idea of like a key and a value, to put it in modern terms. And you would put data in at a key, same way you might do with like a key value store. And then you could also get values out of the tuple space using pattern matching. So it was like a sort of simplified sort of mechanism for doing queries. So as best as we know, Greg took this idea and added that you could store continuations in the tuple space, so that when concurrent processes were accessing the tuple space, not only could they get data back matching on these patterns, but they could also get back a continuation, which was basically the thing that they wanted to do once they had that data, the thing that they wanted to operate on that data with. So, are people familiar with the idea of like a continuation in broad terms? Okay, so it's just like a computational object representing like what to do next. So it could be something as simple as like a function, or it could be a more complicated coupling of a function and the surrounding environment, depending upon how one was going about doing it. So, all right. So yeah, Special K, it was sort of this embedding of Rolang type concepts into Scala. And as we were working on our chain, this sort of need arose to have something like this that was at the sort of core of the Rolang execution engine, as we call it, which right now is the Rolang interpreter. So we'll get into some of the details of that. But what we also wanted to be able to do was to provide a library for any Scala developer to use. And so that was one of the big design constraints when we came up with the current version, which I'm going to be showing today. So it's disk-backed, so that it's persistent. Obviously, this is very important in the blockchain space, but even in a pretty like casual sense, if we put a smart contract in our our computer crashes or the program crashes, we want to be able to pull up the node and be able to have the smart contract still be there and still be able to be run. So and then in the future, of course, supporting the blockchain in Casper, we need to be able to go back and deal with the sort of historical accesses to the store as well. So, when I came to the project about 3 months ago, there was a in-memory implementation of this that was written in RBL, the Rosette base language. I can sort of show you a bit of what that looked like. is the sort of top level here. Are people familiar with RBL at all? Show of hands. RBL. Okay. Part of the story here is that Rolang, the initial implementation, compiles to a, well, it's a top to bottom, it's a compiler that compiles a Lisp-like language into bytecodes, and then there's a bytecode interpreter. It's an actor language. The syntax looks a little bit like Scheme or Common Lisp. We're not showing very much of that on this. You see pseudocode here, but this is like what the language is here. We're defining an actor called namespace. We're setting it up. We're going to put these things in, and then in another two files, there are definitions here for produce and consume. But those are essentially the two main verbs. We don't use put and get when we talk about this. We talk about this notion of producing and consuming. I'll show a little bit of that code just so you can get a taste for it. Let's do produce. So we'll give it a little more. So Kent deserves like a lot of credit, obviously, because he's writing in essentially what is a 25, 30-year-old language when he made this implementation here. But essentially what produce and consume are doing is they're going through the store and they are taking either pieces of data and they're looking for matching continuations, or they are taking continuations and looking for matching data. And we'll get into some of the specifics of that in a second. But I just wanted to give you a flavor of what the sort of initial implementation looked like. So, all right. So this is the Scala Dock for the API of RSpace. So this guy is new. You can ignore him for now. We'll get back to him in a second. But these are the two main verbs right here, and I'll open those up one at a time. First thing we do, though, is we create an instance of the store by calling this create method. Now, how many people are Scala developers? Only a handful. I'll try to walk us through here. The idea here is that we have 4 type variables, one representing channels, one representing patterns, one representing data, and one representing continuations here. Okay, so in RSpace is parametric, we say, in these 4 types. And it means that anybody using this library can use their own types as channels, as patterns, as data, as continuations. There are a couple constraints on this. The constraints is that you have to be able to implement an instance of the serialized type class, which basically means that you can take your type and actually I'll just show you the code of this. It's actually a little easier to understand than the code. So if you have a channel or a pattern type or a data type or continuation type, your type has to implement these 2 functions, encode and decode, right? And that's just taking your type and it's putting it into a byte array, or it's taking a byte array and it's parsing into your type. So for all 4 of those main types that we use, you need to implement this. But basically, the things that go into RSpace, from my perspective, are entirely opaque. So I have no real knowledge of the Rolang innards and the way that we deal with things in RSpace. It's just this sort of extensible API where you bring these instances with you and you tell me, this is how I want to serialize things. That's the first part. And then we have to have a way of pattern matching. I mentioned that before. So you have to be able to match between data and patterns. Which the IntelliJ mode was. So there's another type class called match. And match takes two things. It takes a type representing patterns and a type representing data. Damn, all right. And if you give me a P and you give me an A, you have to also have a function that like matches these two things together. And we don't just return a Boolean value. We don't just say there is a match. In fact, you can do something in the body of your match function to the data and then return a modified piece of that data. So we express that with an option. For those people unfamiliar with Scala or Haskell, an option is like either something or nothing, right? We express that in the type system. So if you were like a C programmer, you might have a null value, but here we do it a little differently. So, all right. So once you have written your instances for those two things, you have to have your serialized instances for continuations, patterns, data, channels, and your match instance for patterns, and then you can start to use RSpace. And so going back to the API docs for a second. We've got our two main functions. This is essentially where the rubber meets the proverbial road. So we'll start with produce. Okay, so you have your store in hand. You've done that create method that I showed briefly before. And you have a piece of data. And you basically want to associate that with a channel. So what we do is we search the store for continuation that may have patterns that match against that channel. And they match the given data here, this piece of data, against the given channel, right? I'm sorry, against the pattern at that channel. So if there is no match already in the store, if there's nothing like a continuation that's already in the store, then we store the data at the given channel. But if a match is found, we don't actually put the data into the store. So all we do is we then pull the continuation out of the store and we hand you back the continuation in the data you just gave us. So you can see here the return type is an option again, and there's a tuple of a continuation and a sequence of data. This sequence here is because we're not just handing you back the one piece of data you just gave us, but we're also handing back other potential matches, because when you're searching that store, there may be other pieces of data already in the store, and when you add that one piece of data, you satisfy that match. So then you'll get back all of the data and you can run that continuation. So there's a persist flag. On the produce side, it probably isn't so obvious how you might use this, but on the consume side, what we'll show in a second, it's actually really critical for actually storing smart contracts in the store. So, all right. If you're lost a little bit, I would expect you to be at this point, but yeah.
And what if something bad happens? The disk goes bad or whatever?
So there's a range of things like that that are probably going to be exceptions thrown by LMDB. And we just basically bubble those up. You'll get the exception. We are not catching exceptions in any explicit way yet. We haven't seen so many of those so far, but obviously, if you're getting things like that, we want to know what they are in their sort of pure, unadulterated form. So we can't necessarily anticipate all the different exceptions that people would get. So that's why we're not recatching them and then turning them into our own error at this point. So, all right. On the other side, we have consume, and this is how you put continuations into the store. And again, we're searching the store, given all the patterns here, we're at the given channels, and we're trying to find a match for the data now, right? Instead of having a piece of data and trying to match that with a continuation in the store, we're now going in with a continuation and seeing if there's data that's in the store. And if no match is found, then we put the continuation into the store. We keep it in the store. But if a match is found, then we return this thing. And again, if a match is found, it doesn't actually stay in the store. You just get that continuation that you just handed back along with the data. So if you want to actually keep the continuation in the store, you have to set this persist flag to true. And that's essentially the mechanism that we use to store smart contracts. And I say that, and it may not really be apparent to anybody how this at all seems like a reasonable way of doing things. As you probably have seen, every read is a write, you know, and every write is a read in some sense. Like we have these two verbs, and they don't really match up to our expectations of normally how a store may work. And part of that is because we're using this sort of old funky model, but really the primary motivation here is that we're trying to support the semantics of like the Erlang interpreter in terms of what it does. So when you think about, obviously some of you are familiar with the sort of hello world example. Boy, this Wi-Fi is slow. I know. And there it goes. It's dodgy Wi-Fi. All right, so like a for comprehension right here, like this part, like we're doing a consume here. Like we're storing a continuation when we do this kind of thing, right? This is using a little bit of syntactic sugar for the contract. But when we use something like this, or in the one with the bang syntax where you do a send, let me pull up another version of that. Oh, is this on master?
If you look in linking, you'll get
Linking has the new one? Yeah. Oh, this is Michael Birch's stuff. I'll show the standard out contract. Because I wrote that, and I know that it's got a bang in there. Right. So for example, when we're sending here, that's a produce. That maps to a produce in the store, right? And so obviously what's happening here is we're looking at the channel standard out. We're producing on that channel with these two pieces of data here, the actual string and then the acknowledgement channel here, right? And then this here, when this is reduced to normal form and plugged into our space here, this is consume with a produce inside of it. So there's a really direct mapping between these Erlang constructs and the produce and consume calls that you saw just back there. So that's why this looks kind of strange. This isn't a storage layer that supports just like persisting blocks in a Merkle tree yet. The thing that we've designed here as our space is really designed to support the Erlang execution environment. So does that make sense to people? Might be a good time to open it up for some intermediate questions before I get too further into this, so that if anybody has any. Yep. Mike.
Got it. Sometimes there's a dependency where there's a need for multiple reads dependent on one write, or there be multiple matches, and then the language throws out those that don't match, or multiple pending matches, and the language throws out the ones that didn't match. Does that make sense? It's a sum in the pi calculus.
Yeah, so you're saying that there's basically the non-determinism in terms of which one gets selected? Yeah.
And that there would be pending possible matches that need to be thrown away.
Yeah. So we kind of do in the innards of, I was just working on this the other day, so. In the innards of, I will answer your question in just a moment, I apologize. Just want to give some context for myself and for the Scala developers who are here. So when we are doing a match, and we're finding match candidates, obviously one way we could do this is we could just start taking things directly out of the store and finding a match. But then the important part is that the things that aren't the match, we actually need to make sure they stay in the store. We can't just take them out and remove them in that regard. So essentially we do a sort of speculative matching where we put together a cache of all of the match candidates, and they're shuffled so that there's a non-deterministic choice. You go through this cache looking for potential match candidates speculatively, and when you find one that satisfies the entire match, then we return that, right? But if there's not, then obviously the store is intact and everything goes on as is. Does that answer your question? Yeah? Okay. Anything else? I mean, if you just don't understand period, it's also a good time to say that, so. Christian.
So what's the format of the actual tuples?
Yes, right. So, I mean, our representation, part of the reason we call it our space is not the real-lang tuple space, is we don't really use tuples per se. You could think of them as 4 tuples of channel pattern or patterns. Well, do channel channel data, which would be like sequence of A, and then you would do like a nested 2-tuple of patterns per continuation. So I'll write on the whiteboard. That would make sense. So it'd be like channel, we'll do seek of A, and then it's like the subtuple here. This would be seek P, K. Yeah. Does that make sense? So this is the data, all the bits of data. And then for each continuation, there is a set of patterns for that continuation. And this is a channel, or this is actually a seek of channel, excuse me. So channels. When you're putting a piece of data in, this is always a singleton list in the way it gets stored, right? Singleton sequence. When you're putting patterns, when you're putting continuations in, this is, if you're going to have a join in row-lang syntax, you're going to have multiple channels. So that's why we have a seek here as well. That makes sense.
And what's a simple example of storing some contract that you run repeatedly or something?
A join is like you're asking what's an example?
No, I just mean of one of these.
Yeah, I mean, a simple example would, if we go back to like what I showed here, mapping that. Okay, so first line, standard out ACK, hello world. Okay, let me see if I can do this. That is a singleton channel standard out ACK. Right now, I'll explain that in a bit. That's what we call a system process. But so that's seek, some AST representation of stood out ACK as the channel here. And then as the data here, it's this whole thing right here. Both of these bits go in there as data. They're not both A's, when we use row length types, it's a sequence of channel. Is that right, Kyle? Yeah. Data, sequence of channel. We use channel for data. Yeah, some row lang type. Yeah. So, that would be stored there. There's no continuation, right? No patterns before the bar here, right? So that's just a single row, as you can think of it, in the store. Second one here, that is a continuation at the channel AC, right? There's some other vagaries of the fact that we've produced a new name in the new scope. I'm not going to necessarily get into them. I'm just going to focus on the core of this. But so we're storing a continuation at that AC channel, and our pattern here is this sort of underbar wildcard pattern here, and then the continuation body here is. Does this go, Kyle, does this go to another produce? Is there another produce inside of that K body? No?
What's stored there is just basically an AST representation of a write to standard out.
Right.
To the standard out.
Right, right.
So the interpreter turns that into a produce call.
How could I not know this? But that's because essentially I've designed the API of this library so I don't have to know anything about the Rolang innards, and that was why. So it's the MacGuffin there. I mean, like, all of the real rubber hitting the road happens in their implementation of match. So Kyle wrote this really fancy matcher for Rolang, and because he supplied that to me as a type class instance, I don't really need to know all of the vagaries. I do know some of the vagaries of what goes on in there, but I
You
don't
wrote
need
the
to know
type class instance.
That's right. I wrote the type class instance. So, yeah. All right. So, Christian, does that sort of satisfy? Okay. Martin?
Is on. So the matching, is it simply looking for all of the names that are matching to the name that you're sending on?
The matcher is really cool, and maybe I'll go over it more on my presentation on Tuesday. But it is basically taking the spatial type checking algorithm with free variables in it and finding a when the spatial type check succeeds, we take all of the free variables that you used and we give the values that were present. So you can write Rolang patterns. You can basically write a Rolang term with a free variable in it, and it will capture whatever value is there. There's this little subtlety, and I'll explain that some other time.
Still, if anybody has any, like, if I don't understand, help me understand questions too. I'm happy to field those, but if not, we can just sort of continue having a gander. Okay, cool. So yeah, I mean, core implementation comes to all of about 300 lines of code, 330 lines of code at this point. This is what sort of like the main semantics are. There's like another class that is like the underlying put and get things and remove things from LMDB. Didn't mention that before, but we use LMDB, the Lightning Memory Mapped database. Sort of came out of the Open LDAP project. This uses B+ trees. It's like compares pretty favorably to common choices like LevelDB, Kyoto Cabinet, Berkeley DB, classic sort of key value stores. The fact that it's memory mapped is really cool. So essentially, they like page out virtual memory, and when you write to that memory, it puts it on disk for you. So it's pretty efficient in that regard. It's getting a little bit of uptake in the blockchain space too. In fact, the LMDB developer It's working on the Monero project, so I would expect that you'll see it in more and more projects as time goes on. So yeah, I mean, I don't know if people are, there's not that many Scala developers here. I don't know if people are really super interested in going through line by line and looking at the code, but essentially, like, the idea here, and when we're producing, we're going to go and look for a produce candidate. And if we find a produce candidate, or we get back this produce candidate, then we are going to remove the waiting continuation from the store. Produce candidate is a continuation. So we're going to remove this waiting continuation from the store. We're going to go through all of those data candidates, and we're going to remove them from the store as well. And then we're going to give you both of those things back. Similar idea here. If there's nothing in the store, then we're going to store that piece of data in the store as well. And then
Are you getting to your sort of,
Are you headed toward things, architectural decisions you need to make, or is this pretty much all solid? Because that's the impression I'm getting, is that there aren't very many questions.
there are some future things moving. Yeah. So, like, for example, we have to support history and rollback, and we've started talking about that in like the last week, for example. So this is like to support Casper, and so I can shed some light on that as well. But I was just going to sort of talk about sort of as it exists today, what it looks like. So, consuming, similar idea here. We go and we look for data candidates and pieces of data that match, as we talked about before. And if we don't find any, then we store that continuation. But if we find some candidates, then we hand them back to you. So that's the general gist of that. So recently we've added system processes. And they don't really, they're part Rolang interpreter, part tuple space at this point. But the idea here is that if we want to write effectful code in what we call system contracts, so not blockchain contracts, but the contracts that run below that, you want to maybe do things like write to standard out, standard error. Now, eventually, we're sort of intending to use object capabilities, but for now, we just have these public names. And so you can send a message to standard out ACK. I'll use the other version of this that's just standard out so you can get the basic idea. But pretty simple. You have this name standard out. It's in the tuple space when you bring up the tuple space. You can write to it, and it's going to print out whatever it finds. Currently, we haven't wired it up to the pretty printer, so what you're going to see is like an AST representation of that string. But eventually this mechanism will be combined with sort of the object capability disciplines so that these will be private names, and only the system contracts will be granted reference to these private names, and they will be able to do things like communicate over the network, do a UDP server, do a TCP server. So if you wanted to write an HTTP server in Rolang that ran as a system contract, you would be able to do that. And blockchain contracts would be able to be granted access to that thing with the object capability reference, but they wouldn't just be there necessarily as public names like this. Right now, we just have them as public names. They have ambient authority, as we say, with object capabilities, but in the future that will change. So standard out is pretty simple. We also have a version that after printing to standard out sends an acknowledgement message as well. That was the one I just showed. Here it is again. So basic idea is that like the tuple space can also be seen as this place where this hub of communication between Rolang and the network and bits of the outside world, that things like our communications layer via Casper will be talking, in the initial implementation at least, we'll be talking to the tuple space using produces and consumes, and then the rollback functions as well. And then there's also, if you want to extend the code, there are these static system processes where there are Scala implementations of these. And we don't actually store real Scala continuations in the store because it's kind of unnecessary. We essentially have like a lookup table where we know at that name there is a bit of Scala code that we can run. So we've written a mapping between those two things. You can run that Scala code, so we have the Scala code that writes standard out. We call that a static system process in the sense that it's kind of hard-coded. We're also working on an FFI, and we call that a dynamic system process. The initial version of that would be like you could load a JVM library, a Java library, a Scala library, and that you would be able to make method calls using hopefully some nice syntactic sugar that's on its way to make this a lot easier, so you're not sending and receiving using strings and things. But we will have a way of basically being able to load in libraries from the outside world and access them through the FFI. This is especially important for cryptography where we don't necessarily want to be the ones shipping that along with the node. We want to be able to, because there are export restrictions on that kind of thing, so it's like, I think so, yeah. So we want to be able to have that part shipped separately. Yeah, so. Okay, I don't have much more to say at this point, but I'd be glad to open it up for more questions. Anyone?
So at some point, we'd like to support the idea of broadcasting, that you send on a pattern rather than sending on a name. How much work would that be to alter the current design to do that?
Yeah, I mean, non-trivial, but, couple sprints maybe.
I mean, can you encapsulate that in the matcher? Is that something that, or is it doing a literal match on the names at the moment? I'm not asking you to do this before Mercury, just to be clear. This is definitely Venus.
I'm going to defer to Kyle on this one. I think he's got an answer.
So the matcher only fires up when you found the same channel. So the matcher is not involved in the channel match is basically a bit match at the moment.
Right.
So they're Rowlang terms, but we came up with a way to normalize them so that all of the structural equivalents fall out and you can do a bit compare.
One other thing I just wanted to point out was, as you said, the format of the continuation is completely irrelevant to you. So this is a really useful library. Any language could use this and store their language's continuation in there and pull it out.
Yeah. So like in some of the examples that we packaged up with the library, I'll show you. So we did this sort of like address book examples, just sort of trivial thing I threw together. It's the kind of thing you often see in like database examples, right? So we have like a notion of an entry in an address book with someone's name and address, email, phone, et cetera. We made like a custom pattern type here. So you're matching against the person's last name, the city they live in, the state. These are all the different candidates for matches that you could write. That's sort of expressed as like a sum type in Scala. And in the example we used here, I wrote a pretty simple class. Reason for doing it a class is that I used Java serialization, which is notoriously hairy. Greg has had terrible experience with it, but I'm sort of trolling Greg a little bit with this example. But the idea here is that this also implements function 1. So entries are our data type. And what we're doing is we're taking these entries and we're printing them out in sort of a nice format. So this is just like essentially an example of what a continuation could be. And generally, the model supports things that have no return type pretty well. I mean, things that return unit, I should say. You can imagine doing more complicated things where potentially you'd have one, but you run that continuation asynchronously in the Rolang interpreter and what they're doing, or in this case, we just run this and it does the effect for us. So yeah, that's like one example of one. Another one that I wrote for the sake of like testing this was what I call a Captor, and it has a little mutable list buffer. This is where it starts to get really hairy, obviously, because when you're serializing and deserializing things that have mutable state, bad things happen sometimes. But essentially, by marking it transient, we're not actually serializing the contents of this thing. We're just putting it in opaquely. And then what it's doing is when we pull it back out of the store, then we are taking all of these entries and we're putting them into the list buffer. So when it goes into the store, there's actually no contents of that thing, and it's not serializing with the contents of that thing. So all this is doing is every time you run this, it's adding the entries that you get into this list buffer. So this is like a way we can basically run this continuation, capture the results, and then inspect the results. You can see here I have this sort of getter here where I do res2 list. Hashcode and equals end up being necessary to implement ourselves here because of the vagaries of Java serialization as well. We don't want these things to, we want these things to essentially not use the default ones that come with Scala because there are dark corners if you do that as well. So, moral of the story, I did this, don't do what I did. And I talked about this when I presented for the community. There are lots of great ways of serializing things. Java serialization, not one of them. We're using protocol buffers. It's like a pretty reasonable choice for this kind of thing. There are some Scala libraries for doing pickling that would also suit the purpose quite well. You could use JSON. That works too. You just take your JSON strings and turn them into bytes and put them in. So nothing's stopping you from doing that. Ah, yes. I wondered when somebody would ask.
The question was about threading.
Right now, we are leaning on the LMDB multi-version concurrency control. So whenever we start one of those produces and consumes, we open a transaction. This basically allowed us to get to releasing a library in under 2 months. We're working on a finer grained locking story for the next, by Mercury, I'll make that claim. Yeah. We're working on a finer grained locking mechanism. A lot of this stuff is going to change as we start to add ability to recall state as well. So that's going to be kind of intrinsically tied to some of the locking story as well. But right now, so if you look at the LMDB locking story, I believe it's basically got like a single writer. And so when you hold open a write transaction, the other guys, can't clobber that. And so that's how we deal with that question for now. But there will still be more to come on that. So. Anything else? All right.